Electromagnetic induction. In this lesson, we shall learn about electromagnetic induction. The phenomenon of electromagnetic induction can be demonstrated by an experiment. Wind an insulated copper wire on a paper or wooden cylinder so as to form a coil in the form of a solenoid. Connect the two ends of the coil to a galvanometer and place a magnet close to it. The reading of the galvanometer is 0 when the magnet is stationary. The pointer of the galvanometer deflects towards the right when the north pole of the magnet is moved towards the solenoid. The galvanometer shows 0 reading when the motion of the magnet stops. This proves that as long as the magnet keeps moving, current flows in the solenoid. If the magnet is moved away from the solenoid, current flows in opposite direction in the solenoid. Thus, the galvanometer deflects towards the left. The deflection increases if the magnet is moved away with greater velocity. If the polarity of the magnet is reversed and the magnet is brought close to the solenoid, then current flows in an opposite direction. The galvanometer accordingly turns towards the left. Faraday observed that current flows in the coil only when there is a relative motion between the coil and the magnet. The direction of deflection in the galvanometer is reversed if the direction of motion is reversed. The current in the coil and the corresponding deflection of the galvanometer can be increased by using a strong magnet or by increasing the motion of the magnet. Increasing the area or the number of turns also creates a strong current in the coil. According to Faraday, when there is no relative motion between the magnet and the coil, the magnetic flux within the coil remains constant. So the galvanometer shows no deflection. But when the magnet is moved towards the coil or vice versa, the magnetic flux changes and an e.m.f is induced in the coil. If the circuit is complete, the e.m.f causes current to flow through it. Based on his experiment, Faraday formulated two laws of electromagnetic induction. Whenever there is a change in the magnetic flux linked with a coil, an electromotive force is induced. The magnitude of the induced e.m.f is directly proportional to the rate of change of the magnetic flux linked with the coil. The direction of the induced e.m.f depends on whether there is an increase or decrease in the magnetic flux. John Ambrose Fleming gave two rules to determine the direction of motion, or the direction of induced current. While the left-hand rule is for electric motors, the right-hand rule is for generators. According to Fleming's right-hand rule, the thumb, forefinger, and middle finger of right hand are stretched perpendicular to each other. And if thumb represents the direction of movement of the conductor, forefinger represents the direction of the magnetic field, and the middle finger represents direction of the induced current. Lenz's law states that the direction of the induced e.m.f is such that it always tends to oppose the cause which produces it. Lenz's law obeys Newton's third law of motion, which states that to every action there is always an equal and opposite reaction. It also obeys the law of conservation of energy. It states that energy can neither be created nor destroyed. Therefore, the sum of all the energies in the system is a constant. Lenz's law is based on Faraday's law of induction. Lenz's law states that when an EMF is generated by a change in magnetic flux, according to Faraday's law, the polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change which produces it.